Welcome back. And now we're going to be starting with centers of gravity. Woo! So center of gravity is basically at the center of our bodies or any body. For instance, this grease, this beeswax that I have here, if I try to balance this anywhere other than at its center, it will not balance. However, if I try to skillfully connect my finger to its center, it might balance. I'm not such a good balance artist. Let's try the bottom. Or let's try something broader like my thumb. Right. Yeah. So my thumb is at its center. I don't think I'll be able to do the top. But anyway, you get the gist. So your whatever you're using should be broad, one. And you should try to balance it at the center. It was better balancing it at the bottom than at the top. Okay? So pretty much that's what you're going to learn about center of gravity tonight. That it's focused on the center of a body, any body, your body, anything or any object. And it is abbreviated as CG. Okay? So I'm going to read now that a body behaves as if its whole weight or concentrated at one point, called its center of gravity, even though the earth attracts every part of it. So the center of gravity of a ruler is at its center, and when supported there, it balances. So for instance, this ruler is 30 centimeters long. I place my finger at the 15 centimeter mark, and pretty much it balances. 30 centimeters long is approximately 12 inches long, and it's also at the 6 centimeter mark, and it's balancing. It's just a little bit rotating on each side, but it's balanced, right? If I move my finger from the 15 centimeter mark to the 10 or the 9 centimeter mark, it's not going to balance anymore. It's literally going to just fall. See? Right. So that is what the picture is showing you right now. Saying if the ruler is supported at any other point, it topples because the moment of its weight W about the point of support is not zero. So when something balances, it's zero. Its moment will be zero. So look at this. It balances. This is a meter rule, 100 centimeters, and it's balanced. The fulcrum is put at the 50 centimeter mark, and it's balanced. It's not tilting right over and falling on one side or the next. In this case, we have it placed at some mark, and it doesn't say where, and the weight of the ruler obviously is still acting at its center. And if you move that pivot there, like in the case, the pivot for the ruler in my demonstration was my finger. And so if you move your finger away from the 50 centimeter mark, it will tilt, it will fall right over. Your center of gravity is near the center of your body, and the vertical line from it to the floor must be within the area enclosed by your feet, or you will fall over. The key word here is enclosed by your feet, right? So you have to always bear this in mind. For instance, your feet, the area here is between this, and for this one it's gonna be between, it's gonna be between your feet, your ankles, and the other side of your foot. So it's gonna be between here and here, so between them there. And for this one, it's much wider, and it's between here and here, right? And this one is smaller, and this one. So this is the smallest one. So therefore, it would, once the base is smaller, once the base that your foot is covering is smaller, your center of gravity will be higher, and it will take you a little bit more time to be balance. You're going to have to find balance. That's how come when you stand on the one foot, you tend to have to find your balance because your center of gravity has risen. And so we're going to look at this, and it should fall between the base of your feet. Well, you know, if I had a ruler, this would be nicer, right? But because the person didn't fall, simply because this was traveling through the base, and I'm going to try to get it as straight as possible. I can't really get straight like that. Let me see. I'm probably cooking up something in my life. She could just probably use blah blah blah. Yeah, I could use it, but I don't want to. We're gonna make sure, right? So once it passes within this perimeter and this between the area enclosed by the foot, then you wouldn't fall. Like for instance, this, you can see the center of gravity here is lowered, and it passes right between the center. It passes right between the base of the feet, the area enclosed by the feet. So you can see it there as well. So I'm gonna try to draw it as straight as possible. And the same thing here. Well, this one is better. The center of gravity is much lower, and the base is much wider. So therefore, you're gonna have less toppling in this case. This is the one, the higher center of gravity. So this person is most likely to fall. Most likely to fall. And this person is least likely to fall. A tightrope walker has to keep their center of gravity exactly above the rope. Why does a tightrope walker have to do this? Right, because if their center of gravity falls outside of that rope, they're going to die. They're going to fall off. If there's no net underneath their body, they will fall and die, go kaput. So the center of gravity is also lowered when they walk with the poles. So the center, instead of being here, the center of gravity will be here, and once it's here, once the center of gravity passes between the enclosed area, the area enclosed by their feet, then they're pretty fine, right? And also remember, the key word is skill. First of all, a tightrope walker must know how to walk on a tightrope, because not everybody could do that. They must know how to keep their center of gravity within the base of their legs. They must know how to keep their balance. And so in this case, not only do they need poles so that they could widen their lower the center of gravity, and also widen the base in this case, they need to have this pretty cool called skill. Now in this case, we know how to find the center of gravity of a regular shaped object. Okay, anything that's regular, you know, like for a square, you know that the center of gravity is easy to find. It's gonna be in the center of that square. If it's a circle, you know it's gonna be in there. So once the it's regular, once it's regularly shaped, you can find the center. However, what about if it's not regularly shaped? Right. So in this case, when I do this example for my kids in school, I will give them something like a little sheet, very small, Bristol board. We call it Bristol board here, and I would tell them just cut something irregular out. Some of them would have to draw it on the sheet, but for me, I'm like, just cut. It's supposed to be irregular, cut it, and then I will cut mine. But of course, I'm gonna do my demo first, because some people would do some kind of outlandish shape and then make it hard on themselves. Start simple. You could go as complicated as you want afterwards, but always start simple when you're starting out something. So for me, I will cut something with like round, something like what's on the video right now. Something irregular. And sometimes what I would do is try to produce a shape for the kids if I'm pressed for time. But if I'm not pressed for time, I will let them cut it themselves. And this one they could make into confetti at the end of class, and of course make sure they clean up after class, right? So that's that. And around the rim now, I would have a puncher, but I think I misplaced my puncher, so I would have to create some holes. Obviously, these holes are not going to be uniform, but you really want to use a puncher so that you have uniform holes, so that you at least control some parts of your experiment. Like for instance, you want to control the fact that you have an irregular shape. You also want to control the string, the mass that's included in it, the setup. You don't want too many things that are beyond your control, because you want to see if using the same hole you're going to find the center of gravity. And I'm going to try to get the holes to look as similar in shape as possible, which I can't get it done, but we're going to hope for the best of this experiment. So I did 3 holes. Usually I would tell the kids to do 5, but 3 holes are fine. And I would have a retard stand, right? So I'm going to show you in the beginning what I do. So here, tighten it. We would hang it on the clamp stand, something that has it hanging. It's moving because I have the AC on and I need the AC. It's so hot here in my country. It's too hot. It's too hot. And then you see I would have it threaded like that, and then I would nicely wrap it around so I could shorten it, and then you could hang, right? And it has a weight on it, by the way. It has a mass, something to hold it down, a mass. And voila, it's hanging, and I'll pull it like that. Now once I have it like that, you try to get the mass to cool down on the swing. Once it cools down on the swing, you make sure you pull it closely together here. And what I would tell some kids from now on, I tell them to put a dye, like a wet dye on the string, so that once they get it to stop swinging, they could just press it on the piece of cardboard and it would have a line there, instead of having to use a pencil, because you could make some simple mistakes with the pencil, right? So you kind of do like this and you have it, you leave a nice line there. So I'm going to turn it to me now. Well, I'm going to show you first what you do. So you have the line here and you make sure it stops swinging, and then as it stops swinging you kind of press it on the manila and you go along the line and you make a soft line with a pencil, right? And you do that. You could do that 3, 5, or how many ever times you want, and you make sure you do it properly. And at some point all the lines are going to intersect, right? They're going to intersect, and that is what you call the center of gravity of the irregular shaped object. And then you would have completed your lab. It's really a fun lab, and I would tell, if I have enough, if the class is small, a small class equal to having enough retard stands, but of late a lot of people have been taking physics at my school and we don't have so many the resources that we have is not enough for our kids, so we have to do something like group work. And nothing is wrong with group work. It's actually really good when you could work in a group, because you get to share ideas, and when you thought you would have known it all, maybe somebody would be like, hey, I have an easier way to do something, or you might see some kind of light shining from your partners and you're like, wow, I didn't even think of that. So I would always encourage people to work in teams, you know, and then maybe later on I would encourage them to work by themselves to build a little confidence, because you know how we go with teams in schools, you know, sometimes there's only one person doing all the work, and that's not how it's supposed to work. Everybody should work together, right? And so this would be my last one, and then you look at it and you let it hang, and when it stops you also draw your line coming down. and I got a good line. It's not perfected, but I found my center of gravity, and what I'm gonna do is use a colored crayon and put a ruler on the lines and run them across, right? So here we are. I'm gonna use green because that was there. It's not my favorite color, but it was there. And then I'm gonna run this line here. Right. So just, this is gonna be straight now because I'm using the ruler. And of course, when there was no ruler, they're pretty much, kind of a little bent. But you get the idea. And I'm gonna put the arrows of leading from where they were hanging from, so you can see holes. And then I'm gonna show you. So here is the center of gravity right in this area. So if the center of gravity is there, then I'm supposed to be able to balance it at this area on my finger. Let me try again. It's the AC, blame it on the AC. It's the AC and the fan that's on. But yay! Anyway, if you're doing this, that is one of the environmental conditions that's against me. But if you're doing this in school, try to not be under the AC. Find somewhere that has no wind blowing or anything. But it should balance. It should balance. Maybe if I put something flat-ended here, better than my finger, but it looks as if so you see? Right. And I think if I put this anywhere other than there, it's gonna fall. Like if I put it here, it's gonna fall. Yes, so my finger wasn't the best choice because it's a rounded tip. So yes, so we actually proved that the center of gravity can be found by hanging an irregular shaped object on some kind of hanging nail or some protrusion, and then allowing a plumb line meaning a weighted piece of thread, wool or whatever it is, string, to hang and rest, and then you just draw a line coming down, right? So cool. So you could do this at home. You don't need a retard stand. You could actually use maybe you might have one of those coat hangers or anything like that. You could use a lot of other things, right? You could even use your finger. Right? You could use your finger and rest it on a table, and then for the other part you would hang the string from there, and you let somebody else write the line down, because if you're using one hand, you're going to be kind of hard. Or you could run a die along the string, piece of wool, and you press it, and then you do it on the next finger. You do it in the next hole, and you do the same thing, and you can see if it works. And you don't have to have a retard stand. Center of gravity. Now the stability of a body is increased once you lower the center of gravity, and once you increase its base, its area of its base, right? So the position of the center of gravity of a body affects whether or not it topples over easily. Like I said, if the center of gravity acts outside of the base, the area of the base, then that object will definitely topple. It will fall. So this is important in the design of such things as tall vehicles, which tend to overturn when rounding a corner, race cars, reading lamps, and even teacups, right? So that's why teacups are nice and fat, because you lower the center of gravity when things become broader, right? So look at these pictures right here. And of course I'm going to mark up, put some annotations on there. Look at this. Center of gravity is here and here. So the area of the base would fall between here, and the area of the base is fall between here and here, right, in this case. But this one, for figure 1, for figure A and then figure B, first of all, two things you must notice. The car in A is slimmer than the car in B, and the car in A is tall. It's not taller, it's just slimmer. Yeah, it's slimmer, so the width of it is slimmer. So because of it being slimmer, its center of gravity is much higher than the center of gravity in figure B, right here. And so the center of gravity also acts outside of the area of the base, and therefore this car will plunk fall. This car won't fall because the center of gravity, which is the orange line, doesn't act outside of its base. So the center of gravity is lowered one, and it falls within the safe zone. Okay. Now when we have tall vehicles, like we know these kind of buses exist in London, in England. I've seen these on television. I've never been to England, but I've seen these on television in London. And they have these upstairs and downstairs buses. And also, you know, those in New York City, they would have those tourist trucks, and they also have upstairs and downstairs. And so, you know, rounding corners would tend to be would pose to be a problem. So the angle of elevation matters whenever you have tall buses. The higher the angle of elevation, the more likely for the center of gravity to fall outside the base of the bus. See? So this one, because the elevation is higher, the center of gravity fell outside of the base of the bus. And in this case, because the center of gravity, no, because this angle of elevation was lower, the center of gravity remained within the area of the base, right? Now, race cars are good at what they're used for simply because they're low. They're low, right? They literally kiss the earth. They're very low. And, you know, the wheels are broad. And they have something that look like this. And they go speed, boom, 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 boom. Right? So, that is what they do. So, they have broad wheels. And they're very low to the ground, right? And the drivers are very low to the ground as well. They look like this, they're broad, and they have their lights. I can't even draw it how it is here, right? And they have the broad wheels that they change in like seconds. I think I was better at drawing it on the side. So let me just do what I know how to do. My drawing skills stop at the point beside. Okay, so moving on. So the center of gravity, types of equilibrium. We have stable equilibrium, we have unstable equilibrium, and we have neutral equilibrium, right? And with stable equilibrium, we could think of a ball instead of a ball. And we think of it like saying if the ball is moved, it will move, right? It will move all over if you're moving it all the time. However, that ball will return to its original position. With unstable equilibrium, we could think of the ball being outside the ball on the hump of the ball. The ball is now upside down and the ball is on top of the ball. And if we were to move this ball, the ball would move, but it wouldn't move to come back to its original position. It will move away from its original position to a new place, and it would eventually stop pending that no outside forces cause it to keep moving, right? So it would stop, and it would then reach to something called neutral equilibrium, where it stays in its new position when it's displaced, and its center of gravity doesn't raise off all. So yeah, so all of these things, unstable equilibrium usually becomes neutral equilibrium when no other forces act upon the body. This pretty much says the same thing that I was saying a while ago. And now we're at the questions. So it says, the figure below shows 3 different positions of a cone. State in which position it is in. 2 will be in stable equilibrium, right? So I would write stable right here, because if the cone is on the broadest area, its center of gravity, which would probably be here, wouldn't fall outside of its base if it's moved, right? Unless you push it so far that it falls over on its side. But here it is stable unless any external forces act on it, meaning if it's pushed really hard, it's shaken too hard, then it would basically fall over. 1 is, I will call it unstable unstable. Well, I would call it neutral. It's a mixture between unstable and neutral. Why? Because if I think about, let's think about no forces acting on it. So I'm going to look at all these cones as no forces, no external forces are going to act on them. So if no external forces act on this, right? Then you could say that this will be stable, right? However, if you say, if a little wind blows or whatever, a little wind, right? Two wouldn't move, or if it moves, it's gonna be like a little bit, go back to your position. However, if this one, if wind blows on one, then it will move, right? And I don't think it will blow right around. It depends. You see, one, it depends. I could tell you for certain that 3 would be unstable because it cannot stay. Like the center of gravity number 1 is acting to this very small base, and if some type of wind or if you know whatever happens, it's going to topple over definitely. So I know that this is unstable, definitely highly unstable. The center of gravity here, I want to say that this could be stable. It also can fall from it also can go to unstable in terms of if you move it, it would rotate in a circular pattern and probably wouldn't end back up in its original position. So I'm gonna say unstable, and I think with my explanation I could keep this. It will be unstable, eventually leading to neutral position. Because if it moves around and it moves into a new position like here, we could all say that it moves and it stayed in that position afterwards, right? So these two are definitely not exactly what they are, but this one, it's toss up, depending on how you explain yourself. Now it says the weight of the uniform bar in the figure below is 10 newtons. So it said the weight is 10 newtons, and if the bar is 100 centimeters long, then at 50 centimeters, the weight must be 10 newtons, because the weight always acts at the center of the body, right? And it's saying, does it balance, tip to the right or tip to the left? Question is, we're going to work this quickly because we're running out of time. We know between here it's 10 centimeters, and because it's 50 minus 40, and between here is 40 minus 10 is 30. So if we multiply the two of them, first of all, we know this is 30 centimeters. If we multiply 0.3 meters by 3, we get 0.9 newton meters. And if we multiply 0.1 meters by 10 newtons, we're gonna get 1, looks like 1 newton meter. So therefore it's gonna topple to the right. I hope we're correct. So let me make sure. Probably stopped taping. Yeah, it did. So it probably stopped taping my face, but whatever, man. I'm just going to calculate this for you. So 0.3 times 3, 0.9. And then we're going to have 0.1 times 10. Yeah, 1. And now why did I change over to centimeters? Simply because, to meters, because remember, when you're doing moments, turning moment, remember it's equal to force times distance. And the force must be in newtons, and the unit of distance must be in meters. So the unit of force must be in newtons, and the unit of distance must be in meters. Therefore, I had to convert the centimeters to meters. And so here it is, and we know the one that is most, the turning moment, that is most, would be the reason. So therefore, if it's more on the right hand side, it's going to topple over, right? It's going to topple to the right. Alright, so I hope this helped. See you around for Our next topic, which is work, energy, and power. That should be interesting. Okay?